All right, so now I'm recording twice. And everybody can hear me okay. This semester I got a microphone, so I'm wearing a mic, so hopefully you guys can hear me better. Last semester it sounded like I was in a tunnel when I spoke. I'm gonna try, I kind of like walking around when I lecture, so I'm gonna be using this board for my lectures, okay? And I'll be writing up here, and there's gonna be some times where I'll actually videotape a solved problem, and I might not use the board, I might use tablets to do that. So what I want to do this morning is go over some important items for this class, and then I'll start lecturing. I'm hoping that you all watch the video I put on Canvas. So that I don't have to spend a lot of time talking about the syllabus, etc. I kind of want to get started on the materials right away in this course. We actually don't cover as many chapters in this course as you did in Physics 205. But it's the material is more abstract, a little more complex, and I spend a lot of time either going through some subtleties in some of the problems we do, or some of the subtleties involving in the concepts. Okay, so we will be covering chapters 23 through 34 in the textbook, plus the chapter on relativity. So that's 13 chapters. I think last semester you guys did 14. Okay, so before I go on, I want to talk about the lab kits. We were going to hand out the lab kits this week, but because of the poor air quality, we have decided to pass them out next week. Okay, so you will be getting an email soon regarding when to get the lab kits. So you'll have to come to campus. We'll have you come into a parking lot. You'll drive into a parking lot with your car. You never have to get out of your car. You just got to show us your ID, your schedule, and I forget what other documents. And then we'll provide you the lab kit. Okay, and the lab kit has really all the material you need for this semester for the labs. You will be doing the labs at home. Okay, we'll see how this works. It's an experiment for us because we did not want you to do simulations because they're useless in a sense. For if you're going to become an engineer, you need to learn how to use the tools that you'll be using later on. Okay, so we will be getting an email actually from our division office regarding what the new schedules are, but it's going to be next week. Okay, so stay tuned for that information. I want to reiterate something about the exams. A lot of you folks went through this at Sierra College last year with the exams, and most of you guys had Chiquel, and I do pretty much the same thing with the exams as she did. The exams will be synchronous, so there's really only 5 meetings this semester where you have to be there at 9:30. Okay, all the rest, the lectures will be recorded, and you can watch the lecture at some other point. Okay. By the way, I want to mention something because one of the tendencies of one of the problems with recording my entire lecture is that you'll have an hour and 20-minute video to watch, and it might be hard to watch a 1 hour and 20 minutes in one sitting. So So what you can do is maybe watch 20 minutes of it without skipping through it, and then come back later and watch it some more. Because we're told we should make our videos short, but it's no different than you watching a bunch of 20, my videos 20 minutes at a time. So instead of sitting through the whole video, you might want to watch watch it in portions. Okay. All right. Anyway, my exams will be live. The dates of the exam are in the syllabus. They're either going to be a Monday or a Wednesday for our group. Okay, I do have a Friday class, And so for my Friday class, those will be on Friday. But for you guys, the exams will be either on a Monday or a Wednesday. I don't have the dates in my head right now. But if you look at the syllabus, you'll see the dates. Okay. Okay. I'm glad some of you guys are looking forward to experimenting with the kids. For exams, I will not do a final. The last exam is a unit exam. It's a short, kind of a short unit exam. It really depends on how much I get into relativity. And that'll only be worth half of the other exams, or maybe it's a little bit less than half, or a little bit less than half of the other exams. Okay. Okay. Having problems creating exam problems that can't be Googled. And so I spent the summer trying to come up with problems that are hard to Google, but we'll see what happens on the exam. That's why my grading policy is different. If you watched the video, you saw my grading policy, and I know people have concerns regarding the grading policy. That when I applied that grading policy to my previous exam, my previous courses, I didn't really see much of a change in the overall course grade. Okay, so I'm hoping that the exams don't end up being overly difficult, but I also don't want to write exams that are easy to Google, because that was an issue last semester. Okay. All right, let me advance here. I will, regarding my lectures, I'm going to email you my PowerPoint notes. There's an issue with my PowerPoint notes, at least for now, putting them on Canvas. So I'm going to just email them to you. And I sent some this morning. I sent it for your labs and for the first 2 chapters of the unit, of our first unit. Our first unit will be on chapters 23 through 25. Okay. Now, it's really important for all of us regarding the exam. Are the exams proctored? No, the exams are not proctored. They're going to be done. The exams are going to be done the same way they were done in year 205 class. Okay, it will be done. You'll be given a file. To print out the file, or use it, use it on your tablet, however you want to do it. You work on the exam for 2 hours and then upload it. Okay, I don't like the proctoring thing because it's very invasive of your privacy. I don't know. It's just kind of creepy. So I don't. At least for now, we're not using the proctoring system.
Professor Calabrese?
Yes.
For the lab, are we going to have a scheduled time for the lab when we're going to meet?
Oh, yeah. So like on Wednesday, I think yours is at 11:10. So we'll meet at 11:10. I'll lecture on the lab, and I'll answer questions you may have on the experiment. It's not going to be. We might not need to meet every week, or I might just meet to answer your questions. Because for the lab, we're only doing. Actually, there are 9 things you'll be turning in this semester in lab. 5 of them are videos. You're only doing 4 written lab reports this semester. The other 5 you're creating video reports. Okay? And so I can foresee there's going to be a lot of times where we meet and you're just going to be asking me questions on the lab. By the way, Tyler is going to set up time to answer questions on labs too. So you'll only have me to ask questions too. You'll also have Tyler. And by the way, if you're going to email me with a lab question or course question, use the discussion board, please. Because what happens is there's going to be more than one of you with the same question. And it's very inefficient if I have to send the same email every single time for the same question. So if you can use the discussion board, that would be great. Now, what I might, if you're not comfortable putting that on the discussion board, I can anonymously copy and paste the question. I will make it it won't look like it's you, that particular person is sending it. I'll post it anonymously on the discussion board with my answer, and then if somebody else asks the question, I'm going to say go look at the discussion board. It's a little bit easier. Okay. Other questions? No other questions? I need to know what you folks need, okay? So if there's something I'm doing that's not working, just let me know. I will try to, do whatever I can to make the material as accessible to you as possible, in terms of understanding. Yeah, and the lab supplies, we will send you an email regarding the lab supplies. It was postponed until next week because of the unhealthy air quality. And you'll just be driving up in your car. You need to show your ID and your schedule, and I forget what other documents. And then we'll just hand you one. Okay. Tutoring options. Yeah, I'll give you a tutoring schedule. I'll email you a tutoring schedule because I got an email right before class started regarding tutoring schedule. If you do want to set up a Zoom meeting individually with me, if you have questions, we can do that too. Okay, we can make appointments. I'm supposed to only have one student help hour this semester because I'm online, but I actually set up 3 of them. Okay, so I'm going to be doing Monday, Tuesday, Thursday from 1 to 2. And if you go on Canvas on the home page of our course, there's a link to my office hours, and there's a password you have to add. Okay, and my office hours, I didn't set it up through Confer Zoom. I set it up through Zoom. Okay. So these will be my office hours or student help hours this semester. Okay, I guess I should use the term student help hours. I'm glad most of you folks have been able to log on. I was looking at the news this morning. A lot of folks cannot log on to Zoom. They're having problems. Oh, question regarding the lab. Another question regarding the lab kits. Two questions. Okay, the tutoring. Patrick, which tutoring center are you referring to? Are you referring to the one in the library? Because there's 2. So we normally have our own tutors. Yeah, and we don't usually use we don't usually have tutors going to assign tutors to the library. We have our own, and I know there's one person that has 4-hour time windows. Okay, let me give you the after class or sometime today our tutoring schedule. It's basically the same tutors as in the S105C. Okay, yeah, once in a while we'll have a tutor in the library. And you're right, none of tutors there probably have a physics background, but the ones that you want are the ones I'll refer you to later on today. And it'll be done on Zoom, so please use last year when we went online, our tutors were pretty lonely. They didn't have a lot of questions to answer. Okay. Another question, I want to make sure that coming Tuesday is not. Yeah, there's no lab kit pickup tomorrow. The lab kits will be next week, okay? Which actually works out fine because we haven't actually built the lab kits yet for our class, okay? In fact, we were still waiting on 1 or 2 pieces of equipment. So next week, you'll come and pick up lab equipment, you will get an email for that, okay? And it won't come, first it'll come from our division office, and I'll send you an email. So you'll probably get 2 emails regarding the lab kits.
We get to choose what day we pick it up on, or is it going to be strictly like a certain time and a certain day?
It'll be a certain time and certain days. Like, my guess is we're just gonna roll the schedule we had this week to next week. So there was a Tuesday from 3 to 7. There was a Wednesday morning one. And I think there was a Thursday one, if I remember correctly.
Those schedules will be posted.
Yes, you will get an email from our division office with the schedule.
Perfect. Thank you.
Okay. Oh yeah, by the way, since I got to mention this, a little bit off topic, but a lot of students are going. A lot of high school students are going to be online, and they're going to need tutoring. This is your if you want to make money, probably you might want to try to tutor students, like high school students, if that's something you want to do. I think that especially if you pick the right regions, like and I'll say Granite Bay, for example. Okay. If you want to tutor students privately, it's a good opportunity this semester to make some money. Okay. All right. Let me switch my PowerPoint here. Give me a second. I gotta switch my share. Hold on a second.
Racy,
Yeah.
I also want to know where the recorded videos and lectures are going to be uploaded to.
Well, since we're using Conferred Zoom, I'm assuming you should be able to see them on Conferred Zoom.
Okay, so like it's going to post it after.
Yeah, it should say after. If not, I'll give you a link.
Okay, thank you.
Okay. The one that I'm videotaping right now, and I noticed mine stopped for a second and then started again. So the one I'm videotaping right now, I'll put on YouTube. Okay. So you'll have 2 sources, but probably the one from, you want to look for the one from Zoom first. Like what happened this morning with the video from my camera. I instead of clicking on the PowerPoint, I clicked on the my video and it shut off the video. So like there's going to be 10 minutes missing. Okay, but not the Zoom one. Can you all see the PowerPoint?
Yes.
Okay, good. So I didn't have to change the screen share. All right. So I guess I went a little bit longer than I thought I would. So what I want to do today, and I won't get to this, I want to talk about charge, and I want to talk about Coulomb's law and examples. Give an example of Coulomb's law. I do have another example of Coulomb's law where I approach the problem a different way, and I'm going to videotape it. I'm going to just create a video of it. And it's not necessary that you know how to use the other technique, but it gives you an idea of how we use some of our ideas in subsequent topics. Okay. So any more questions before I get started? Okay. Yeah, you will see this twice. You'll see the screen sharing, and then you'll see me in the corner. That's because I'm screen sharing it. So if I remember when, that's okay. It'll be fine this way. All right. So again, this is how our course is broken up into 5 units. The last unit is shorter, so the exam is worth less. And it's nice to have an exam that's worth less on the final day of the semester. Okay, puts less pressure on you folks. So these are our goals. That's what I want to talk about today. So I want to talk about charge first. What is charge? This is something new. So far in Physics 205, the fundamental measurements that you focused on were mass, length, and time. And physicists, when they talk about a fundamental measurement, they put a bracket around these letters. And everything that all the quantities that you learned last semester were derived from these fundamental measurements, where they talked about force, where you talked about velocity or acceleration. They're all derived from these fundamental measurements. And I'm being very general and very abstract because you can also assign units to that, right? These are just measurements, and then with each of these measurements, you can assign a set of units. Well, there's another fundamental measurement in physics. It's called charge. I want to say a few things about charge. We're going to talk about it from experimental or empirically, at least. Okay, it was known from the 600 BC. I think the person's name was Thales. That things get charged. And really wasn't until around the 18th century when the idea of positive and negative charge was developed. And really the idea came from Franklin, Benjamin Franklin. Okay. He did a lot of experiments in electrostatics, and he came up with the idea of positive and negative charge. And he introduced the concept of conservation of charge. And then around 1897, J.J. Thomson measured the charge to mass ratio of the electron. It wasn't really until around the late 1800s where the idea of the electron and the proton, or at least a positive charges and negative charges, were considered as particles. So it was all the way until then. And in 1909, Millikan measured the charge of the electron and then showed that charge is quantized. What does that mean, that charge is quantized? I mean, charges come in discrete quantities. The basic unit of charge is 1.602 times 10 to the minus 19 coulombs. I'm using SI unit. That's the basic unit of charge. And all charges are based on multiples of this value. Okay, I'm not telling you the whole truth, okay? Because we're not going to talk about quarks in this class. Quarks have multiples of 1/3 or 2/3 of this number. Let's not worry about that, okay? We're not at that point yet. So for us in this course, all charges are basically multiples of this number, and it could be positive, negative, or zero. Was there a question? Sorry. Okay. So they're either positive, negative, or neutral. So the proton is considered a positively charged, so this value, so the charge on the proton is plus 1.602 times 10 minus 19 coulombs. By the way, there's more digits after that, okay? You don't have to memorize all the digits. The electron is minus this number, and then the neutrons have no charge. Or really, I should say the neutron, the total charge of the neutron is 0. Neutrons are made up of quarks, and each quark has charge, but the sum of the two adds up to 0. Charge, in one sense, is like mass. It's a scalar quantity. It's conserved. Charge can be positive or negative. Mass can't. Mass is only positive. Charge can be positive or negative. And as a result, charges can exert attractive and repulsive forces. Masses only exert attractive forces between each other. That's the big difference between mass and charge, right? Mass is a scalar. Masses exert forces on each other. Mass is conserved. And there is a basic unit of mass. Okay. But the difference is, mass is always positive. Charges can be positive or negative. Okay. The fact that we're talking about quantizing means that the charge comes in multiples of this value to a discrete number. Of course, if you have a lot of charges, the difference between 1 trillion charges and 1 trillion and 1 charges is not that big. It's going to be this value, but that's hard to measure. If you measure the charge on 1 trillion particles, and then the charge of 1 trillion and 1 particles, it almost going to seem like a continuum of charges just because you have so many. But they are discrete. So if you have 2 charges that are negative and 2 charges that are positive, E means the charge of the electron. When you add these two, you get 0. So charge is additive. There's like mass. Okay. We're going to do a lab called the properties of charge. It's just let me just do a quick demonstration of charging objects. By the way, one of the things I really don't like about teaching the class online is the lack of demos. This is an old balloon, so it doesn't have as much helium as it used to have. Hope it'll stay up. And I'm going to take a PVC rod, okay, and I'm going to rub it with fur. That's not real fur, okay. Oh yeah, we're going to give you fur, but it's not real fur in our lab kit. So I'm going to charge this. And by the way, by convention, when I charge this rod becomes negatively charged. This was a convention based on Franklin, like the balloon theory. Okay, there's my balloon. And so, wait a minute, why did it attract? Why is it attracting the balloon? The balloon isn't even charged. Why is it attracting the balloon? I charge the rod. The balloon is not even charged. Why is it attracting? That's strange. Because if I were able to charge the balloon, negatively charged, the balloon would repel it, and if I made the balloon positively charged, it would actually attract it. And it's very hard to do. But I didn't do anything to the balloon. Why is it getting attracted to this rod? And this is where we have to understand the properties of charge. So let me explain this one, and it's going to be related to your lab. The balloon is an insulator. Is it inducing a charge? Essentially, yes. It's not. It looks like magic. You're going to be doing this, right? I mean, you can take a balloon, rub it on your head, all right, and it'll stick to the wall. Okay. It works great with the helium for a balloon, by the way. So when you look at the material the balloon's made out of, it's an insulator. And when you have an insulator, the electrons are not free to move. When you look at the molecule, now I'm not going to get too technical. I will get more technical in the lab. When you have an insulator, the electrons aren't free to move. And in a lot of molecules that make up objects, not all, if you look at the distribution of positive charge and the distribution of negative charge, their centers kind of coincide. And so you get an even distribution of positive charge and even distribution of negative charge. So they're simply neutral. But if you take a rod, like I did, that's negatively charged, and I bring it by the balloon, what do you think is going to happen to this positive charge and this negative charge? Well, the negative charges don't like each other. I like saying it that way. And so what's going to happen is you're going to have a distribution, a redistribution of charge. Maybe like this. You've polarized the charge. In fact, you're inducing what's called a polarization of charge. That's the term induction. Okay, and it's temporary. It's not permanent. You can do it permanently too. There's ways. We'll talk about that in a lot. But you're separating the positive and negative charge. So now this guy's close to this. But guess what's going to happen? If this positive charge is closer to negative charge, well, if this guy's closer, that guy's further, they're going to be attracted to each other. Okay, that's what's happening. So you've polarized the charge in the molecule. That's called polarization. Now, there are some molecules in nature that are already polarized, like water. And you'll see the effect is more dramatic when you use water. So, an example, you get a real narrow stream of water, and you run it, and then take a comb and rub it on your head, or take a balloon and rub it on your head, and bring it, not at the top of the stream, at the bottom, actually bring it at the top of the stream, and you can see the deflection of the water. The stream has to be pretty narrow for it to work, because if you got a big, thick stream, it's too much water, too many water droplets, and you won't get to see the deflection. So really what you're doing is polarizing charge. There's a video I would like, so when we get to the lab, there's a video I would like for you to watch in the lab regarding this topic. And so when you get to the lab, you'll see in the lab, in the modules for the property of the charge lab, the first thing is the video I would like for you to see. You don't have to see the whole video. It's the demos that I want you to see. Okay, and the instructor talks about properties of charge. He talks about Coulomb's law too, but he talks about properties of charge. So that I'd like for you to see that, because I'm in a small room. It's hard for me to do demos, and he has a lot of demos on this topic. Okay, so charges have interesting properties. This is one of them. You can polarize charge, and you can get an uncharged object to be attracted to a charged object. And that's always true. An uncharged object will always be attracted to a charged object. The effect is even stronger with metals. Why is it stronger with metals? Because you have a small fraction of the electrons in the metal that are free to move around anywhere within the metal. So let me try one more demo while I'm at it. Here's a can. And by the way, I always use a negatively charged rod because it works better. I have more luck with it. So let me rub this PVC rod. The electrons in that can are free to move. I can do this with a positively charged, and I won't do it because in the interest of time, but this works better. You can't see that? me see if I can change the, hold on a second. I can fix that. The PowerPoint's in the way, isn't it?
That looks good.
Okay. Okay, you can see it now? That's one of the issues doing this thing online and live. That was too fast. But I mean, you can see it was much more dramatic. It was a stronger effect because the electrons in the metal are much freer to move. And so, like, that thing was uncharged. There was a strong attraction. All right, let me go back. I have so many things open, it's hard for me to see. Hold on a second. I need to adjust my display. All right, everybody can see stuff? Can you guys see everything? Okay. And let me get the chat up so I can see the chat. I actually do like 3. Question regarding ferrous materials. Well, actually, ferrous materials are not as good as something like, you're talking about like iron. Copper and silver, those work the best because they're the most conductive. Okay, that's better. Okay. So, interesting experiments involving conservation of charge. You can take 2 electrons, I'm sorry, not 2 electrons. An electron and its antiparticle. What the heck is an antiparticle? You take an electron, and a positron, that's the antiparticle. They're opposites. In what sense? Well, they don't have opposite mass. They have the same mass, but they have opposite charge. And they have other properties that are opposites of each other, which I will get into. If you send them into each other at a high enough speed, they will collide and they will disappear. What's the total charge you had at the beginning? 1 plus negative 1 plus 1 is 0. They collide, the 2 masses disappear. And we say, wait a minute, mass is conserved. Yeah, later on this semester we're going to learn that mass can be converted into energy. Energy is conserved. And so what happens is they collide into each other and they form 2 particles called photons, which is basically a light particle, 2 light particles. So we will conserve energy. Okay? And we will conserve charge. In fact, the opposite can occur too. You can get 2 photons that come in, collide with each other, and 2 particles appear. You can get pair production when 2 photons collide into each other. These have been observed in the lab. This is an example of conservation of charge. It's weird, but it happens. Hard to do. Okay, so I want to talk about the main topic here. I need to look at the time. It's Coulomb's law. And Coulomb's law describes how these charges interact with each other. The force of attraction. What you see on the screen is the equation that represents the magnitude of the force between two charged objects. Okay? And that's something you gotta remember. That equation, the way I have written it, represents the magnitude of the force between two charged objects. I should write it like this. I'll label it 1, 2. Force on 1 due to 2. Okay, if I write it as F12 is a force on 1 due to 2. That's the convention I will use. And so this represents the magnitude. Notice I'm putting absolute values on the Q's because I want the magnitude. By the way, K is called a Coulomb constant. K is similar to the gravitational constant. Look at that equation. You guys have talked about gravity. Same form, right, as the gravitational force. In gravity, these are n's. You still have the r there. Remember, r is the distance between them. It's not a radius. And then K is the difference here. So the Coulomb constant is about 8.99 times 10 to the 9th Newton. I won't put the dash there. Meter squared per Coulomb squared. Do you remember what the gravitational constant was? That was the gravitational constant. Oops. Minus. Look at the difference between those two in terms of size. This number is 10 to the 20th times as bigger. What does that say about this force relative to gravity? And so you're right, it's way stronger. Okay, it's way stronger. Let me look at these comments. Yeah, this is an action at a distance force. It's a 1 over r squared force, and it does act like gravity. Okay, it does act like gravity. Okay. And yeah, you're right. General relativity is a more complete way of describing gravity. We're not going to get into. I mean, we can't get into that, but you know, the one thing what I want you to look at is focus on the form of this compared to the form for gravity. Okay. And in fact, this is not complete either. This doesn't always work. I will tell you. I will tell you when this works and when it doesn't work. Okay, in a minute. So this is a huge force. When you study chemistry and you talk about the electrons in the atom, and you want to do a calculations for describing the electron in the atom, you completely ignore gravity. Okay? I mean, you completely ignore it. You only focus on electric force. And some relativistic, special relativistic effects, but we won't get to that. Okay. And you just use Coulomb, and you actually kind of apply Coulomb's law. Okay. You actually talk about the electric field. Now, in order for this to work, and I'll say this now, in order for this to actually be valid, the charges can't be moving. Now, this is true when the charges are moving. If this charge starts moving relative to this charge, there is a lot of complications that come in. First of all, if this starts moving, moving charges create magnetic fields. So now you not only have an electric force, but you also have the magnetic force. But now you have time-dependent forces because this is accelerating, and time-dependent fields create time-dependent fields. You cannot use Coulomb's law anymore when these objects are moving. Okay, so when we do problems involving Coulomb's law, we're going to look at really what's happening at instant in time, or we're going to say they're fixed. Because this is really not valid. In fact, you've got to be correct, what works in every case is by describing the force on this object in terms of something called the field created by this object. It's like just like you guys talked about gravity. Yeah, it is true. You can use magnets, although that's a magnetic effect. The electric and magnetic fields are related to each other. But yeah, you can overcome the Earth's gravitational field with magnets. That's true. Okay, so this doesn't always ring, and in fact, this works with point charges. Okay, so if we can treat the system as a point charge, we can use this equation. All right, so there are some limitations, and a lot of times the books don't describe them. But the fact, if they're moving, you start getting special relativistic effects that we won't cover them in this class because it's somewhat complex. Okay. What happens when you take into account relativity? I can show you and I'll do it when we get to relativity. What happens when this one of these is moving? You get bizarre results. You get really bizarre results when you have charges moving relative to each other and use Coulomb's law. Okay, they get results that don't make sense. So again, Coulomb's law is valid for a stationary point particle, or when you have an object that acts like a point particle. When do you think an object will act like a point particle? Well, when the object has spherical symmetry. And I don't know if you did a problem like this in Physics 205, where if you have an object that has spherical symmetry, you can treat it like a point particle. And I don't know if you did that proof in that class. It depends on how much time you have in class. Okay. So that's really when you can use this law. The objects have to be stationary, and they have to act like point particles. Okay. It cannot explain the case when there's a charge, when the charge experiences an electric force in the absence of other charges. I can actually have a charge here. I can have a charge in space, and no other charge is near it, and that thing will experience a force. That cannot be described by this. For example, I can have a radio antenna producing electromagnetic waves far away. This will experience a force too. It'll be small, but it'll experience a force. Okay. So yeah, it has its limitations. Now, we can there's a couple of ways to write this K constant. It can be written this way too. You can write K as 8.99 times 10 to the plus 9. It's also written as 1 over 4 pi epsilon naught. Epsilon naught is 8.85 times 10 to the minus 12 with these units flipped. Oops, these units flipped, sorry. Okay, let me check, let me see how good I am on time. Okay. All right, so this is called a permittivity of free space. And for well-behaved insulators, this is for vacuum, right? This is the value of vacuum. For well-behaved insulators, the permittivity is a multiple of this. This times some number. And that number, that constant, is called a dielectric constant, and it depends on the material. We'll learn about that later. What this thing represents is how well the fields penetrate a material. The bigger the permittivity, the less the fields will penetrate the material. In fact, in a metal, it's very interesting. In metal, if you put a metal inside a field, inside of it, and I'm talking about a solid piece of metal, it will set up a field that cancels the field outside, so there's no field inside the metal. That's what it does. Yeah, the Coulomb, you're right, this assumes a vacuum. We're pretty much always going to be working in a vacuum. Okay, that's a good point. We'll be working in a vacuum. And if we're not, it's basically we're going to multiply this by kappa. It'll make this number smaller. For metals, this is going to be infinite. I'm sorry. Did I say it right? Yeah, it'll be infinite. Okay. So that'll make K 0. That'll make the field inside 0 for a metal. Let me do a couple comparisons. Okay, or let me do one comparison. I want to look at the gravitational force between two electrons. I want to compare the gravitational force between two electrons and the gravitational force between two electrons and the electric force between two electrons. Let's say I have two electrons that are a meter apart. The distance doesn't matter. So we have two electrons. And I want to calculate the ratio of the gravitational force to the ratio of the electric force. So it's going to be G and you know the R's are going to cancel. Oh yeah, we need to know the mass of the electron, don't we? So the mass of the electron, somebody actually measured it. Not correctly, okay? Is that value. Okay, so put in values. And I'm going to suppress the unit because otherwise I'm going to run out of space. This ratio is approximately 10 to the minus 42nd. Just gives you an idea how small this force is compared to this force. Where you need to have, really to experience gravitational forces, you need to be dealing with big objects. With the electric forces, you don't. I mean, look at that, it's such a huge difference. Now, I want to represent Coulomb's laws of vector, and I'm going to show you how to represent Coulomb's laws of vector. And I'm not going to do problems using this idea. Okay, I will do a video where I will show you, we will use this idea to solve a problem. But I really am not going to use it. And the reason why is solving Coulomb's law problems this way is completely unphysical. It's just, it now becomes a math problem. So it gives you no physical insight. And I like for you guys to develop physical insight. Okay. And we'll see where this idea comes from when we start talking about electric fields. Suppose I have two charges. Okay, so we have Q1 and I have Q2. And I want the force on 1 due to 2. And we're going to write it like this. No absolute values. I want the actual force vector. And then I'm going to define the vector that goes from the source. If I'm looking at the force on that guy, what is the source producing the force on that guy? Well, this is the source. And so I'm going to draw a vector, a unit vector, that points this way. It's a vector that points directly from the source of the force to the object in question. And we'll call this object, we'll call this one the test charge. The one we're studying, we'll call it the test charge, and you'll see why we call it the test charge later. Okay, so I can write it like this. So all I have to do then is plug in this number, the actual value of this number, the actual value of this number, and then the actual value of this number. But I have to figure out what my unit vector is. Okay, I have to write mathematically what the unit vector is, and I can do that. The problem is, to me, is that it's not physical. Okay? When we're studying forces, really what we should be doing when we're studying force problems, guess what we should draw first when we do a force problem? What should you draw first when you do a force problem?
Force diagram.
Correct. So I want you to be able to draw your free body diagram when we do it, but you can't get away from that. Okay. And then the other thing that students forget in this course is that students forget that force is a vector. So you have to actually draw your free body diagram and resolve forces into their x components and their y components. Students forget that. A force is a vector. Okay, the math doesn't care. Vectors treat the same way whether you're talking about a force in physics 205 or a force in physics 210. you have to take the vectors, resolve them, and then sum the forces. Okay?
Professor Calabrese,
Yeah.
I got a question. You know when you have like masses acting on different mass, like a force acting on a mass, isn't there going to be an equal and opposite reaction, right?
Yes.
Yeah. How does that go for, let's say, electrons?
Oh, you're talking about Newton's third law. How does Newton's third law work here?
Yeah.
Okay,
Like,
that's a good question.
electrons are pretty much massless to a point of degree, right?
I'm sorry?
Never mind. Go ahead with that question, the original question.
Suppose I have a big object, the charge is 10 coulombs. By the way, 10 coulombs is a monstrous amount of charge. That's probably the amount of charge you get in a lightning bolt. Okay, but just for our purposes, we'll just use this. And then we have a little object, and let's say this mass is 100 grams. And we have a little object, we'll call this Q1, we'll call this Q2, and the charge on it is 10 to the minus 5 coulombs. It's 1 gram. Which experiences the bigger force? Well, here's the equation for the force. And I'm going to write it as the magnitude. This is the distance between them. Now, if I want to find the force on this charge due to that charge, I got to put 10 coulombs here and 10 to the minus 5 coulombs here, right? If I want to find the force on this guy, I put the same 2 charges here at the same distance. So, yeah, they're the same. The forces are equal but opposite. It obeys Newton's third law.
Okay, yeah.
Okay? The forces are going to be the same. It obeys Newton's third law. Up to a point. Same thing with gravity. It obeys Newton's third law up to a point. If the objects are really far away, you will see that whether you're talking about gravity or whether you're talking about electric force, Newton's third law is not valid. Okay. Yeah, if I switch the charges, the forces will remain the same, right? If I switch these two, I mean, however I want to do is switch the charges or just ask for the force on this guy, the force on that. It's the same equation, right? I use the same equation both ways. The only thing in here is the product of the 2 charges. So the force will be the same. That's Newton's third law when the objects are close to each other. But when the objects are far away, it doesn't work. I'll give you an example. Okay. I'll do it with gravity. Let's look at the planets in our solar system. And you know, for example, that our planet has an attraction to Jupiter or any other planets. So let's suppose Jupiter explodes for some reason. Okay? Assume that Jupiter explodes. Are we on Earth going to feel the effect instantaneously?
No, it's kind of like lightning, like strikes, you could see it, you don't hear the sound, but it's kind of the same thing. There's distance that different things like light and sound travels.
Yeah, that information is going to take time to travel towards the Earth, right? Right? It's going to take time for that information to reach the Earth. So the time rate of change of momentum of Jupiter is going to be the time rate is not going to be the same as the time rate of change of momentum of the Earth. So where's the missing momentum? It turns out that the missing momentum is carried by the gravitational field. The same thing with the electric field. Okay, with electricity. We're going to define the electric field. And the electric field reconciles the fact that when you have objects really far away, Newton's third law doesn't really work when objects are really far away. It works when objects are close to each other, but not really far away. And the field carries that information. Okay. Whatever momentum is missing, it's carried by the field, because fields carry momentum. They carry energy, they carry linear momentum, and they carry angular momentum. And we'll see that later on this semester, at the end of the semester. Yeah, ultimately, if you add them up, it's just with a lag. And that lag, but the dp dt is what's missing, right? There's a lag time. But when you measure dp dt, which is really it's if you take the dp dt of the field plus the dp dt of the Earth, then it's going to be equal to whatever the dp dt is of Jupiter. And that lag causes an issue. It's the time lag that's there. Okay, if that information can be transferred instantaneously, it'd be a different story. Are we okay with that? For now, we're going to assume that the objects are close to each other. Yeah, it obeys Newton's third law. But you just got to realize that when the objects are real far away, this don't work. The idea of the field always works. And that's what we're going to talk about next time. I think, let me see how much time I have. Oh, couldn't get through the example. Are you folks okay if I make two, because it's already 10:50, videos of two different problems? I'm going to do, and if you're not, just tell me where to go. Are you guys okay if I actually solve this online? Okay, I'm going to give you this example. I'm going to solve it two different ways. So I'm going to create two videos. Okay? And what I want you to do is ask questions next time if you have problems with it. Okay? Yeah, yeah, it's okay. I know I have a class after this. That's the thing. I have the lab for my Friday class in a few minutes, so I have to get ready for that. Okay. So if you have questions that I ask on the discussion board, I'll create the video, and I'll try to add captions to it too, and I'll post it on Canvas. I'll probably post it in the discussion board. Okay. So if there's anything you guys need, let me know. And I'll look into the WebAssign issue. Okay, don't pay anything for WebAssign. Please don't pay anything. Okay? Because if the WebAssign, they should have contacted me right away. I don't know what's taking them so long. If they don't contact me right away, I will just create a new course. Okay? Yeah, you guys have already paid something, right? That's why I gotta say don't pay anything. All right? Because you took Physics 205, you paid for the multi-semester one. You can look at the assignments. The problem is, I got a couple people already started. The numbers will be different when I switch. Yeah, those of you who already started, if you want to go ahead and keep doing it, go ahead. I think what I'll do is I won't. Yeah, we'll see what happens. Just continue working on the free trial. Okay, if you start already. I apologize for the screw up. It's probably my fault, but yeah, Patrick, you have another 11 days. Can you just hold off today? Because why don't you print out the homework, print out the assignment? Because what will happen is just print out the homework and work it. Don't turn anything in. No, you don't. You shouldn't need to pay anything, because if you use the access code, if you had an access code that was for multi-term. Okay, if you use an access code, that access code was for multi-term, and so you should be in the system for the entire lifetime of the edition, which is going to end soon. But you guys should be okay. At some point, the publisher is going to say, "Hey, go to the 10th edition." Okay, but that won't be you. It will be the new 205 students. Okay. Otherwise, we'll be very upset with them. We've been your customer for years. Well, we've been WebAssign's customer for years. I guess Cengage too. WebAssign used to be separate from Cengage. So I actually don't like the fact that Cengage bought them out, because everything's slower now. Any other questions? I hope I answered everybody's questions. Was this presentation mode okay for all of you? Okay.
Yeah, this worked great. Thank you, Calabrese.
All right, sure. I just want to make sure it works out. I mean, this is again, we're in a weird scenario, so. All right, so I'll see you all on Wednesday. I'm already losing my voice. Hey.
All right, you take care.
All right, you too. And I gotta end this.